Welcome to Mickey Study Circle channel. In this video, we shall see how to perform the stress analysis of a bar of constant area which is subjected to the varying loads using the Ansys Workbench. We'll move on to the problem statement. We have a bar of 800 length which is attached rigidly at the endpoints A and B as shown in the figure here. Forces of 30 kilonewtons and 60 kilonewtons are applied as shown. So as you can see that 30 kilonewton is tensile and 60 kilonewton is compressive. If the Young's modulus E is 200 MPa, determine the reactions at the two ends. Also, if the bar diameter is 25 so here the word diameter indicates that the bar is circular in nature. Compute the stresses and change in length of each portion, that is AC, CD, and DB. So this is the problem statement. So we have got a bar of uniform cross-sectional area, that is throughout the length of the bar of 800 the diameter remains 25 itself. And then it is having the same material also. That is why the Young's modulus is also the same. So with this data, we need to compute what is the deformations in each sections of the bar when it is subjected to the varying loads. So you can just see that how the two loads of different magnitudes and directions are applied here. So 30 kilonewton is tensile for the portion AC, whereas it could be compressive for the portion CD. And again here for the portion CD, the 60 kilonewton could be a compressive load, but whereas for DB it could be the tensile. So in this combination, we have got the varying loads, and now we need to compute the deformation, reaction forces at the support, and also the total elongation in each portion of the bar. But since both the ends of the bar is fixed, the total elongation will be equal to 0. So we'll see how it could be solved using the strength of material approach. And also we'll assume the Poisson's ratio to be 0.3. So first let us compute the reaction force. So let us assume that P is the reaction on the bar from the support at A, and then the forces acting on each portion of the bar are as shown. So we'll be computing the portions of the bar as AC, CD, and DB. So in the portion AC, we'll assume that the reaction force is negative. That is why the magnitude here is minus of P into L, that is the length of the portion AC, which is 275 divided by A into E. Next is the portion CD. So here we are having a load of 30 newtons, 30 kilonewtons added to the existing reaction force P. And again, this is also compressive in nature, so a negative sign. And the length is 150 divided by area of cross section and the Young's modulus A into E. Similarly, we have got the shortening of the portion dB. So there it is 30 minus of P because it is compressive in nature into 150, that is length, divided by A into E. So these are the different values considering the deformation in the bar of length 800 at each section. So when I add up this, all this will be equated to 0 because the bar is constrained with the supports at both of its ends. So this is how I've taken 1 by AE common from all the portions of the bar and then subjected this to the total elongation equation, which is equal to 0. So upon solving, we do get the value of P, which is nothing but the reaction force at the support A in the bar, to be equal to 8.4375 kilonewtons. Suppose if I just take up the equation like 30 minus P or minus of P plus 30, so I'll be getting the reaction at the support B, which is equal to 21.5625 kilonewtons. So these are the reaction forces at the supports. Next, let us compute the values of the stress. So considering the portion AC, we have got the mathematical model for stress given by the formula P by A. So the value of P here is minus of 8.4375 into 10 to the power 3 newtons. And the area is computed by calculating the uh, mathematical model, that is pi into r square. So the diameter is 25, so the radii will be equal to 12.5 so that is the area. Upon substitution, we get the value of sigma in the portion AC, which is equal to minus of 17.1887. So the negative sign indicates that the stress induced is compressive in nature. Next, we get the portion stress induced in the portion CD. So the sigma is given by P by A. and the p is minus of 30 plus p, so we have got the value there for the p. So area is this. Upon substitution we get the value to be equal to minus of 78.3042 newton per mm square. So this is the stress induced in the portion cd. Next is the stress induced in the portion dB. So we'll substitute the values. So this is the magnitude of P in the portion dB. This is the area of cross section. So the maximum stress that is induced in the bar is 43.9268 Newton per mm square. That is tensile stress. And we do have got the compressive stress with 78.3042 Newton per mm square. So this is about the calculation of the stress in each portion of the bar. So we have got two compressive stresses and then tensile stress in the portion dB due to the varying loads that is applied as shown in the figure for the bar. So now let us compute the values of the deformation in each portion of the bar. So first portion is AC. So we do know the magnitude of the load P, and upon substitution into the mathematical model, that is P into L by A into E, we get the value of the deformation, which is equal to minus of 0.02363 mm. Similarly, in the portion CD. So these are all shortened due to the application of the compressive forces. The magnitude here is minus of 0.05873 mm. And next is the portion dB where a tensile load is applied. So we do get the value of elongation in the dB, which is equal to 0.08236 mm. So we do know that the sum of the deformations upon all the sections will be equal to 0, because the bar is subjected to constraint at both its end and it is not having any portion for the elongation to occur. So the total deformation will be equal to 0. So if you just add up the deformation from AC, CD, it is equal to dB with a negative sign. So negative and positive, they get cancelled, which is equal to 0. So this is the value of the deformation. So we have seen how to compute the reaction forces, stresses, and the deformation values using the strength of materials approach. Now let us see how to compute the parameters using the Ansys Workbench. Thermal properties in the problem statement, we'll select the static structural analysis system. So just double click on static structural and the project file is going to open. And let us rename this file into stress analysis of bars. So first let us go for the engineering data. Double click on engineering data. So by default, the material given to us is structural steel, and the property you can just verify. So structural steel is selected and the property you can see that it is 211 pascals. So we can just change this to psi or megapascals. So it is 2e5. So we can just cross check if it is exactly 2e5 or are there any other values. So it is 2e5 and the Poisson's ratio is zero point 0.3. So we can just keep it as it is. We'll just close the engineering data. We are not defining any new material as we did it in the previous video. Now let us go for creation of the geometry. So select the geometry from the project file, and the geometry is going to open up in the designer modeler mode. Select the xy plane and keep it perpendicular to the observer by clicking on this icon, that is look at face. So you can just see that the plane is ready for sketching. So you can just see that the SI unit for all the drawings here is in meter. So let us just change the units to millimeter. So select millimeter and now go for sketching mode. Select the line option and let us draw the three portions of the bar as given in the problem statement. So H indicates that it is the horizontal line. So we have simply drawn three lines because three portions are required, that is AC, CD and DB. Now let us go for dimensions. Select general. So take the measurements of all the three portions of the line and we shall edit that here. So the first portion is having a total length of 275 mm as given in the problem statement. So enter 275. So the next portion CD is having a length of 150 mm. So enter 150. And next, the final portion is having 375 as the length. So this is the length that is assigned. So you can just see that it is not fit to the screen. you can just press F7 or click this icon zoom to fit, so that you get the object fit to the screen. So after you have defined the line and then defined the dimension for the line, just click on generate. So it has defined three different portions of the uniform cross sectional area bar. So now we need to assign the line sketch for this line. So for that we'll go for concept, select lines from sketches. So select the first line until apply, and next let us select this portion of the line, change this add material to add frozen, and then click apply again. So select the next portion, that is db, and ensure it is add frozen until apply. So the purpose of adding frozen component here is, if suppose if this was to be a composite bar, then we have to select this to be different materials, but since it is the same material, we are going to just click on add frozen, so that there is no gap between these two elements and they're all perfectly frozen. So just go and click generate after having defined the parameters. So you can just see that we have defined a part from the line now. So we need to assign the cross section area. So go for concept, select cross section. So since it is circular bar, select circular cross section, and here any parameter you can define. Either you can directly enter the area, or if other parameters of moment of inertia is given, that also could be entered. So here for me the diameter is given in the problem statement, which is 25. So let me feed the value of the radii, which is equal to 12.5. Click enter. So the 12.5 radii circle is ready. Click generate. So the area is now changed to 490.87 square, as you can see here. So we have defined the cross section, so we need to assign the cross section. So we have clicked generate now. So we'll go for line body. From the tree outline, select line body, and you can just see that cross section is not selected. So click on this and select circular one, and then click generate. So you have assigned the cross section for this particular line part that we have created. So in order to view that as a 3D model, just go for the view option, select cross section solids. So you can just see that the circular bar is ready with the frozen joints at these 2 points. Okay, so this is the end point A, this is the end point B, and these are the points C and D where the loads are applied and it is frozen. So you can all just see that it is a uniform cross sectional area circular bar. So the geometry is created. So we'll just close this geometry module and go for the model. So double click so that we are going to open it up. So the progress can be seen here in this part of the screen. So now the software is going to import the previously generated model. So this is the workspace wherein we can go for meshing, applying the loads and all this. So the model is appearing as a line. So in the display option, select cross section. You can just see the cross section of the body. So this is how it appears. So now go for geometry, select line body, and here by default it has taken the structural steel. So we have not defined any other new material, so just select structural steel. You can just see that the line body is applied with structural steel by default. If any other new material was defined, then select line body and apply that material. So now let us go for the mesh and right click and select generate mesh. So by default it is going to create a discretized model. So again go for display style, select by cross section. So you can just see that the cross section is appearing now. So time for us to apply the boundary conditions and the loads. So go for static structural and come to the environment menu, and the environment menu, let us select fixed on the vertex. So select this vertex until apply. So a fixed support is assigned to this vertex or this point of the bar. Next again select fixed and select this vertex till apply, and again you can just see that fixed support 1 and fixed support 2. So the green tick indicates that the parameters are fully defined. So the supports are assigned. Time for us to apply the forces. So there is in the environment, there is something called as force. So select the force option and then select define by the components. And in the x direction, it is 30 kilonewtons first. So 30,000 newtons will apply. So it is asking the direction. So we need to select the direction. So for that, we'll just select the point C here. Okay, so this is the direction of the force. So click apply. So this is the direction of the 30 kilonewton load. Next, again select force and then select components. So the x component now it is minus 60 kilonewtons, that is 60,000 newtons. So it is asking the direction. So select this point till apply. So since you have already entered it as minus, it is taking the direction as this by default. Okay, so these are the forces that is applied. So we have applied two supports, that is at end A and B, and then two loads of the forces, that is at point C and D on the circular bar. So just click on solution and select solve. So it is going to solve the mathematical model and the solutions are ready. So let us generate the solutions. Go for solution, select insert, beam tool, select beam tool. Again right click and select evaluate all results. So open this and you get the direct stress. So you can just see that the values of the stress are shown here. So the maximum value is 43.96. Okay, so this is minus 78.36. So obviously there will be some variations because in the theoretical calculations we would have rounded off the area to 2 or 3 decimal places and the system would have rounded off to the different values. So obviously in the decimal point there will be some variations. So this is the compressive stress. So here is the compressive stress in this region. So again go for geometry, go for display, select display style by cross section. That can be seen in the deformation later. So this is how the stress distribution is going to occur. Go for beam tool, select insert, deformation total, right click until evaluate all results. So this is how you get to see the deformation. Deformation for the deformation. So the maximum deflection, that is 0.082427. So this is the maximum deflection that we have got. So that is the tensile component of the deflection. So the other values are seen here. So now we need to compute the reaction forces. So let me go for solution, select insert, and then select probe, select force reaction. So it's asking where the force reaction has to be computed. So select fixed support 1. Okay, then tell retrieve or evaluate this result. So you get the value of the reaction force at this end, that is 21,562 newtons or 21.562 kilonewtons. Again, let me go for beam tool, select insert, go for solution, select insert, select probe, and select force reaction. So let me select the fixed support 2 now, and then right click until retrieve this result. So you can just see that I'm getting the reaction force at this end shown along with the direction, that is 8437.5 newtons or 8.4375 kilonewtons. So this is the reaction force. So we have computed the values of the stress, the total deformation, and also the reaction forces at the supports using the Ansys Workbench. So now let us go for solution or static structural. Go for display and let us see how to take the images of this. Select the deformation now. So in the home menu there is something called as images. So go click on this images and select image to file. So select show preference dialog, click OK, and then you can just save this as a deformation. So this is the deformation snap being saved as a PNG file. Click save. So now let us see how it appears in the respective folder. So this is how you take the results from the Ansys Workbench for your report making. Now let us take the direct stress. So go for images, select image to file, current graphics display, click OK, and then save this as the stress plot, click save. And then force reaction. So this is at one support, and the force reaction, this is at the other support. So similarly, you can take the uh, snap of the force reactions as well. With this, we complete the video which details about the performance of the stress analysis of a uniform cross-sectional bar subjected to varying loads. Thank you all for watching.